We will wait for a few minutes more and then we will start. I think we should start now. Can you see my screen? Hello? Can you see my screen? Can you see the presentation? Okay, so let me go back to the presentation. So I once again welcome you all to the introduction session on atomic and molecular physics NPTEL course being run for January 2023 session. Myself, Vivekananda Naik, I am a PMRF PhD research scholar in the Department of Energy Science and Engineering, IIT Delhi. So today we will discuss a few problems regarding the uh, lectures that we have covered in the 10th or 11th week. So let's start with our first problem of the day. The problem is, for an applied magnetic field of 1 Tesla, It is observed that the G-man components of a 450 nanometer spectral line are 0.0116 nanometer. Find the value of E by M from the above data. Now, what we have been given in this question, for an applied field magnetic field of 1 Tesla. So here it is given the magnetic field strength B is equals to 1 Tesla. It is observed that G-man components of a 450 nanometer spectral lines are 0.0116 nanometer. So here lambda is given. Lambda is 450 nanometer, 450 nanometer, and the G-man components of the splitting is also given here. The splitting is 0.0116 nanometer. So splitting is nothing but d lambda, which is given by 0.0116 nanometer. So what we have to find here? We have to find the value of E by M. But we know in case of this G-man splitting, or in case of G-man splitting, that is when an atom is placed in an external magnetic field, a single spectral line gets splitted into a number of spectral line. So this is the spectral line and this is the splitting. And the if you consider in terms of frequency domain, the frequency of transition is given by d nu is equal to Eb by 4 pi m. This is same as Larmor frequency. If you remember, Larmor frequency also we take Eb by 4 pi m. So here the change in frequency is Eb by 4 pi m. Now if we convert this, if we go from frequency domain to wavelength domain, then what we will do? We know E is equals to how much? H nu, or equal to Hc by lambda. So nu is equals to c by lambda, that is frequency is equals to velocity by wavelength. So when you take derivative of frequency, it will be how much? The frequency derivative will be d nu, and that will be equal to minus c by lambda square into d lambda. So this is the conversion from frequency domain to wavelength domain. But we know in frequency domain the change in frequency is Eb by 4 pi m. So but here in the question we have given with the wave number, and we have given with the wavelength and the splitting, which are also in wavelength units, that is in nanometer. So what we will do here, we will write this d nu in the place of d nu we can write minus c by lambda square d lambda, and then the expression will be minus c by lambda square d lambda equals to Eb by 4 pi m. Eb by 4 pi m. In our calculation we can remove this negative sign, because we are simply we want to simply calculate the value of E by m, so sign is not important here. So when you calculate E by m, so what will be E by m? Then E by m will be c by lambda square. This c will be coming that side, so c by lambda square into d lambda into 4 pi by b, into 4 pi by b. So from this we can get this. So here this is the E by m ratio we want to determine, because in question it is given to find the value of E by m from the data. So the value of E by m can be given as c by lambda square into d lambda into 4 pi by b. So what will, so when we put all the values, we know the value of c. We have the value of lambda, d lambda, and b is 1 Tesla. So when we put all these values, we can calculate the ratio of E by M. So when we put here C in 3 into 10 to the power 8 divided by lambda is 450 nanometer. So here we can simply write 450 because here lambda square into lambda, here it is lambda square, here it is d lambda. Lambda is in nanometer and d lambda is also in nanometer, but here lambda square, so here will be 1 nanometer present. So when we convert it to meter, we will multiply only 10 to the power minus 9, and in place of d lambda we can simply put this value because 1 nanometer gets cancelled, so we can put here 0.0116 into 4 into 3.142 divided by B is 1 Tesla. So please put all these values as I have done here and tell me what is the answer, what will be the ratio of E by M. I will wait for 5 minutes, then we will proceed to the next question, or if you have any doubt you can ask me regarding this question. Did anyone calculated the value? So what will be the unit of this ratio? Yes, it will be coming somewhere near this value. You are right. So what we will get if we put all the values the unit of this E by M ratio will be how much? The unit will be coulomb per kg, because E is in coulomb at mass in kg. So if you put all the values, it will be around 2 or 1.95. It will be 1.95 into 10 to the power 11 coulomb per kg. So this is the desired value of E by M, that is charge and mass ratio. Can anyone tell me what is this ratio otherwise called as? E by M has some name. Charge by mass. It is known as specific charge, which is also known as charge by mass. So this is for electron. The ratio of electronic charge by its mass is 1.95 10 to the power 11 coulomb per kg. So basically in this question, it was given in a magnetic field. The spectral line of certain wavelength, that is 450 nanometer, is splitted into G-man components, and the lines are the splitting are 0.0116 nanometer apart. So from this value we can calculate the value of E by M. So this is the value of the magnetic field which is given, that is 1 Tesla, and the wavelength is 450 nanometer, and the change in wavelength, that is the splitting, is 0.0116 nanometer. So when we put the expression for change in frequency is in case of G-man effect, so it is d nu is equal to Eb by 4 pi m. So since we are given with the we are given with the wavelength domain, so we need to convert from frequency domain to wavelength domain, and in that case we can put the relation between wavelength and frequency, that is frequency is equals to velocity by wavelength, where c is the velocity of light here, and when you calculate the change in frequency, that is d nu, so d nu comes out to be minus c by nu square d lambda. Then when we put all the values in case of d nu, it is minus c by lambda square d lambda equals to Eb by 4 pi m, and then uh, from that we can calculate E by M, which will be C by lambda square into d lambda to 4 pi by b. So when we put all the values, because we are given with all the values and we put all the values, we will get the ratio, which is 1.95 into 10 to the power 11 coulomb per kg. um, does anyone have any doubt, or I will proceed to the next question then? Okay, so let's go to the next question. This is a very easy question. The question gives, uh, for three 2s half state, write the values of quantum numbers n, l, s, and j. So the we know for spectroscope notation, it is n 2s plus 1 l j. This is the spectroscope notation, and here what is given, the state is 3 2 s half. So when we compare all these, so we can easily tell that n equals to 3 here, and in case of 2s1 we have 2, so 2s plus 1 equals to 2, so it will give s equals to half. We got n equals to 3 and s equals to half, and another term here l, and here it is s. So we know for s, l is 0, because for the nomenclature is such that for s l is 0, for p l is 1, for l is 2, the state is d, like that. So here l is 0, and the remaining is j, and j is here half. Clearly we can see here it is half, here it is j, so here j equals to half. So it is a very easy question. So simply from the state we can calculate all the quantum number values. So here it is written as n, l, s and j because it is a single state, but when we are considering the ls coupling we write it as small l, not small l, we write it as capital L, capital J, like that. So this is the value of n, l, s and j for the state 3 to 3 to s half. These quantum numbers, n is principal quantum number, l is angular momentum quantum number, or orbital angular momentum quantum number, s is spin angular momentum quantum number, and j is total angular momentum quantum number. So I think there should not be any doubt in this question. So we should proceed to the next question. The question is, calculate the possible values of Jz for the 2d 3 by 2 state of the electron. So here, so from the state it is given 2d 3 by 2. So the state is 2d 3 by 2. So from this notation we can easily say that here j is 3 by 2, and we know that for j, for 1j we have 2j plus 1 mj values. So for if j is 3 by 2, then we have, then how much mj values we have? We have 2 into 3 by 2 plus 1, so that is 4. So we have 4 mj values. So mj is nothing but jz, that is the component of j along the magnetic field direction, where z is the direction of applied magnetic field. So here we will have 4 mj values. So when we compare with j equal to 3 by 2, then the jz values will be how much? There will be 4 jz values, and these are nothing but minus 3 by 2 minus half, half, and 3 by 2. So these are the 4 values of jz. But here you even calculate the possible values of jz. Here these 4 values are mj values, and in case of jz we know jz is the unit of angular momentum. So here we will write h cross in all these, because jz has the unit of angular momentum and h cross has the unit of angular momentum. So here the values of jz will be minus 3 by 2 h cross, minus 1 by 2 h cross, 1 by 2 h cross, and 3 by 2 h cross. So if j has 3 by 2, then there will be 4 jz values, and these 4 values are minus 3 by 2, minus half, half, and 3 by 2. Do you have any doubt regarding this question? Anyone? Is it clear to all of you, or I should explain it again? So we can proceed to the next question. The Here the question is, find the most probable distance of electron in the ground state of hydrogen atom. So here we want to calculate, find the most probable distance. So what is the most probable distance? Um, so here we will take the help of the probability distribution. With the probability density, we had talked about it in the previous interaction sessions. So here the question is, find the most probable distance. That is, most probable distance means probability is maximum. So probability will be maximum. So in that case, This is the radial probability. So we will have p as p is a function of r. So if we take derivative of p with respect to r, then if since it is most probable value, then the derivative of pr with respect to r will be 0. Then first we will calculate pr, and then by taking the derivative of pr, when we equate the derivative to 0, then we can get the value of the then we can get the most probable value. So what we will do here, it is a ground state of hydrogen atom, and the probability density depends only on the radial radial wave function of the electron in the hydrogen atom, so which is r10, which is r10. So r10 equals to how much? R10 is 2 into 1 by aq, root of aq, e to the power minus r by a, where a is Bohr radius, that is r0. We then I'll call it at r0, or alpha 0, maybe somewhere it can be written. So this is the radial wave function, that is r10 is equals to 2 into 1 by a, root over of aq, e to the power r by a. And we know the probability density pr is given by r10 square into r square. This is the probability density of the electron in the ground state. For ground state we are putting here r10, because for ground state n equal to 1. So if n equal to 1, L will be 0. So from RNL, if we write it R, N and L, then it will be R10. And we know wave function has some other part, which is also known as y spherical harmonics, that is y00. So here it is RNL and y, L and M. So for L equal to 0, M is also 0, only one value. So for hydrogen ground state, the values will be R10 and Y00. The value of Y00 is spherical harmonics, and the value of Y00 is 1 by 4 pi root. So when you put all the values, then the total wave function of hydrogen atom is how much? The total ground state wave function of hydrogen atom is psi 100, that is NLM, is equals to R10 into Y00, and that is equals to 1 by pi aq root over to the power minus r by a. Because here you can see, here it is 2. So when you take this 4 root over of 4, then it will be 2, and this 2 cancels out, and this pi comes inside this square root. So it is 1 by pi aq root e to the power r by a. However, we don't need here, we simply can take the help of only the radial part, because the probable probability density is given by r square and uh, r square and r10 square. So when we put this value, then what will be the probability density? Then the probability density pr will be how much? Then the probability density pr will be how much? Pr equals to r square into r10 square. R10 is 2 into pi aq square root e to the power r by a. So it will be 4 by a, it will be 4 by aq e to the power minus 2 r by a. Now this is PR, and the if you take the derivative of P, so this is PR r square. PR is r square, which is also this is equal to r square r 10 square. So for most probable for most probable position, it will be maximum. So d by dr of PR will be 0. So when you take derivative of this, then it will be how much? If you take derivative, it is r square, and it is 4 by aq e to the power minus 2 r by a. So the derivative will be, if you make r square aq e to the power minus 2 r by a into minus 2 by a plus 2r into 4 by aq e to the power minus 2 r by a, and this is equals to 0. So if you take derivative, then this derivative is 0. So derivative we, so keeping r square is here, r square fixed, e to the power minus 2 r by a into 2 by a, and again taking the derivative of r square, it will 2r, and the remaining will be present. Then when you take common 4 by aq e to the power, if we take common 4 by aq e to the power minus 2 r by into r, so it will be how much? 4 by aq e to the power minus 2 r by a. What else we can take common? We can also take common 2r, because here it is minus 2r square, here it is 2r, so you can take 2r common. So we can take 2r common. So 2r common we take. So it will be how much? This will be minus r, minus r by a plus 1 will be 0. So here we take this term we took common, 2r 4 by aq e to the power minus 2r by a. So when you take this common, that it will be 1 minus r, 1 minus r by a. So when you equate it to 0, then this term will be 0, and the bracketed term will be minus r by a plus 1 equals to 0, minus r by a equals to minus 1, r by a equals to 1, r equals to a. So r is nothing but the most, r is nothing but a distance. So since we are taking the derivative of so since we are equating the derivative to 0, it gives the most probable distance of the electron. So when you take the derivative and we are taking the ground state wave function, so the most probable distance of the, so the most probable distance of the electron in a hydrogen ground, in the hydrogen ground state, is a, where a is nothing but the, where a is Bohr radius, where a is Bohr radius, and its value is roughly 0.53 Armstrong. So this is the Bohr's theory of hydrogen atom. We had calculated the values of R, and R is Jd square by 2 epsilon 0 NH, and this R is The r is also the most probable value, and this most probable value is a, that is the bore radius for ground state. So this was the question. In this question, we had to find the most probable distance of electron in the ground state of hydrogen atom. The ground state of hydrogen atom means the n value is 0 and L value is 0 and m value is also 0. So the ground state will be psi 100, and if we decompose into two parts of the wave function, the total wave function can be written as radial part and another is angular momentum part, that is spherical harmonics. So it will be r10 into y00. So this r10 for hydrogen ground state is 2 by aq root over e to the power minus r by a, and for finding the radial probability density we can take only the help of the wave function, radial wave function, that is r10, and the probability density is given by r square r10 square. So when we take derivative of this r square r10 square and equate it to 0, we can get the most probable distance, because for most probable distance the probability is 0, the derivative of probability is 0. So this is the value of so this is the value of uh, so this is the value of ra0 r10, and so we put here the square of r10, 2 by aq root over, the square is 4 by aq, and it is e to the power minus 2 r by a, and r square is multiplied according to the formula, that is probability density is r square into the radial wave function square. So when we take the derivative and equate it to 0, then the derivative will be r square 4 by aq e to the power minus 2 r by a into minus 2 by a plus 2r into 4 by aq e to the power minus 2r by a, which will be equals to 0. Then by taking common the second term, you can take common and it will give 1 minus r by a equals to 0. So it will be r by a equals to 1 or r equals to a. So the r equals to a for ground state, for ground state for ground state, r equal the most probable distance for electron is a. So for most it can, so we can say that for most of the times the electron can be most of the times the electron can be found at the at a distance a uh, from the nucleus, where a is Bohr's radius and it is 0.53 angstrom. And in the previous class, if you remember, we had solved another question, and then the question was what is the most probable distance of the electron in the fast excited state of the hydrogen atom. So in case of fast excited, if you want to calculate in this way, you need to calculate the probability density, and for probability density we need the radial wave function, and in that case the radial wave function will be r20. If we are talking about the fast excited state, it will be r20, and if you take r20 mod square and multiply it with r square and then equate the derivative of this term with respect to r20, then you will get the value of r equal to something, and that will give you the most probable distance for fast excited state of hydrogen atom. But simply we can calculate, easily calculate, uh, if you remember the formula for, add another slide. So if you remember from Bohr's theory of hydrogen atom, the value of r was n square s square epsilon 0 by pi m jd square. So this is so so we can say r is direct proportional to n square. So here r is proportional to n square, and for ground state n equal to 0, and for ground state n equals to 1, n can't be 0. Ground state n equal to 1, and for fast state n equal to 2, like that. So here r will be how much? R will be proportional to 4a0 when we talk about n equal to 2. So simply we can say r equals to 4a0 is the most probable distance of the electron in the fast excited state. Fast excited state. So in the fast excited state, the most probable distance, the most probable value of the position of the electron is 4a0. Similarly, for second excited state, it will be 9a0, like that. Is it clear to all of you, or you have any doubt regarding this question? Is it clear to all of you? Or I should explain it once again, because it is a important. It is an important question. This type of question, the question I was discussing with you, that is the probability, most probable distance of position of electron in the fast excited state. The same question came in the GATE exam in the 2020, in the 2021 exam, 21 year. The same question had come in the GATE exam. The most probable value of electron position of the electron in the fast excited state. And if you know this trick, then you don't have to calculate, do a long calculation, because here what we are doing, we are taking the derivative, and then the derivative we are equating it to zero to get the value. Simply, if you don't want to do all these calculations, you can simply write the, you can simply use the formula r diet proportional to n square. So if for fast excited state, so for ground state it is n equal to 1, so it is a0, and for fast excited state n equal to 2, so that is second level. So for the second level is uh, r equals to 4a0, like that. So this is the way. Let me explain it once again. This question says, find the most probable distance of electron in the ground state of hydrogen atom. And from most probable distance, the probability density, the derivative of probability density with respect to r will be 0. And we know the probability density is given by r square into r10 square, where r10 is the radial part of the ground state wave function. And for hydrogen, the radial part of the ground state wave function is r10, 2 into 1 by aq root e to the power minus r by a. And when you put these values, then PR will be how much? R square into 4 by aq e to the power minus 2r by a. And if you take the derivative and equate it to 0, the derivative will be r square 4 by aq to the power minus 2r by a into minus 2 by a plus 2r into 4 by aq e to the power minus 2r by a, and this is equals to 0. So when you take 2r 4 by aq e to the power minus 2r by a as common, that will be 1 minus r by a equals to 0. So r by a equals to 1 and r equals to a. So r equals to a gives the most probable distance of electron in the ground state of hydrogen atom. So we should proceed to the next question now. The question gives, what is the 0 point energy of a particle in a three-dimensional infinite potential well? So 0 point energy means the ground state energy for a particle in three-dimensional infinite square well. Can anyone tell me what is the energy of the particle? That is, what is the ground state energy of the particle in one-dimensional infinite potential well? We have discussed it several times. Can anyone tell what is the 0 point energy or ground state energy of a particle in one-dimensional infinite potential well? That is, for in a single dimension for up to some length, the potential is zero, and the potential is infinite everywhere. So if you remember, the for one dimensional potential, the energy En given by n square h cross square. Sorry. So the expression for energy for one dimensional infinite potential box is En equals to n square h cross square by 2m a square, where a is the length of the box, that is, if r equals to or r or x equals to 0 to a, the potential is 0, and any other position, that is whether r is less than a, r is greater than a, or r is less than 0, the potential is infinite. Generally the shape of the potential is like this. V is equals to 0 in this region, that is, the region is from 0 to a, and outside this region the potential is infinite. And we had solved the Schrodinger's equation, and from Schrodinger's equation we get the energy values. The values of energy is n square h square by 2m a square, where n is the quantum number state, n is the quantum number representing the state, and here n can't be 0, because for n equals to 0, the wave function becomes 0, and if wave function becomes 0, we know if wave function is 0, the particle can be present there. However, we are considering here the particle is inside the box. So if the wave function is 0, so n equal to 0 is not acceptable. So here n equals to 1 is the ground state. So for ground state, it is n equals to 1, and the energy is known as 0 point energy, or E1, which is h cross square by 2m a square. Similarly, in three-dimensional infinite potential well, what we can write, if particle is present in a three-dimensional potential, then there will be three components, that will be x, y, z. So n will have three components. One will be in x direction, another will be y direction, and another will be in z direction. So the energy expression then is converted into En equals to nothing but nx square plus ny square plus nz square h cross square by 2m a square. So like the one dimensional potential well, where the value of n was starting from 1, here also the value of n will be starting from 1. So here the value of nx, ny, nz will be 1, 2, 3, like that. So for ground state, or the 0 point energy, so you simply, we can write it E0 or E1, whatever you may be writing here. So for ground state, that is 0 point energy state, nx, ny, and nz will be 1. So all these three numbers, nx, ny, and nz, is 1, because only then the waveforms will not be 0 and it will be minimum energy, and we know that ground state of a system has minimum energy and it has maximum probability. So the ground state will be corresponding to the energy value, which will be coming from the values of nx, ny and nz as 1. So when you put these values, nx square plus ny square plus nz square h cross square by 2m square, then how much value we get? We get e0 equals to 1 square plus 1 square plus 1 square h cross square by 2m a square, which will be 3 h cross square by 2m a square. So the sorry so the 0 point energy of a particle present in a three-dimensional infinite box potential is 3 h cross square by 2m a square. So this question was, what is the 0 point energy of a particle in three-dimensional infinite potential well? And we know for a one-dimensional infinite potential well, the energy value is En equals to n square h cross square by 2m a square, where n stands for the quantum number representing the state, and for one dimensional infinite potential well, the value of n starts from 1, that is it is 1, 2, 3 or like that. So the 0 point energy becomes h cross square by 2m a square. But however, in case of a three-dimensional potential box, there are three numbers on which the energy depends, and these are nx, ny and nz. Similarly, we can write here E is equals to nx square plus ny square plus nz square h cross square by 2m a square. And for 0 point energy or ground state, all the values of nx, ny and nz is 1, because only then there will be minimum values, and if any one of them is 0, then the wave function becomes 0, because the wave function is not in particle in one dimensional box. The wave function was how much? 2 by a root over sine n pi x by a. It is in 1D. If you consider in 2D, it will be 2 by a sine nx pi x by a into sine ny pi y by a. Similarly, this is in 2 dimension. Similarly, in 3 dimension, sine will be 2 by a to the power 3 by 2, because there will be 3 2 by a raw root over. So it will be sine nx pi x by a into sine ny pi y by b into sine nz pi z by c. If we take a equals to b equals to c, then these three terms will be equal, that is a equals to b equals to c. Then in that case only, when a equals to b equals to c, we can write here the energy value of the energy eigenvalues are nx square plus ny square plus nz square h cross square by 2m a square. And when put the values nx, ny and nz equals to 1, then we get the 0 point energy is 3 h cross square by 2m a square. So this is the ground state. So this is the ground state energy of a particle present in three-dimensional infinite potential box. That is that is 3h cross square by 2m square. So can anyone tell me if nx, ny, and nz is one for all are one for ground state, then what will be the values of nx, ny, and nz for the fast excited state of the particle? Can anyone think of it? If the ground state for three-dimensional potential box is consisting of the values nx, ny, and nz equals to all one, then what will be the fast excited state and what will be the energy of the fast excited state? That is, what will be the values of nx, ny, and nz for fast excited state and the energy values. So here, what we can write, if it is the ground state, nx equals to 1, ny equals to 1, nz equals to 1. So it has only one combination and it is 3 e1, where e1 is, we can take this value as e1. Yeah, this is e1. So e1, if you take this h cross square by 2m square as e1, then the values will be 3 e1. Similarly, if we consider the fast excited state, the fast excited state will be the fast excited state will be how much, the value, any value of any of these values of nx and ny and nz can be 2. So here nx equals to 2 and ny and nz will be remain the same, that is 1. So it will be how much, 1 square plus 1 square plus 2 square, because here we know the in case of energy expression we are taking nx square plus ny square plus nz square. So when nx equals to 2, ny equals to 1, and nz equals to 1, so it will be 1 square plus 1 square plus 2 square, that is 6. So it will be 6 e1. But in another case we can take ny equals to 2. So we can take here nx equals to 2, nx equal to 1, ny equals to 2, and nz equals to 2, nz equals to 1. So in that case also, if you take nx square plus ny square plus nz square, it will be 6 e1 again. So there can be another combination where nx equals to 1, ny equals to 1, but nz equals to 2. So it is also 6e1. So for these three combinations of nx, ny, and nz, we are getting the energy same, but the wave function will not be same, because in case of wave function here it is nx, here it is ny, and here it is nz. So if a and b and c are not equal, so in if nx equal to, it will be sine 2 pi x by a, or it will be only pi y by b and pi z by c. But when ny equals to 2 and both nx and nz are 1, then nx here it will be sine pi x by a, sine 2 pi y by b, and sine pi z by c. So in this case, the wave functions are different, but the energy values are same. So these basically this condition is called as degeneracy. So for fast excited state, there are three discrete wave functions, but energy is same. So the degeneracy is 3. But here degeneracy is 1, so we can call it as a non-degenerate state. But here degeneracy is 3, so we call it as a degenerate state. So because for fast excited state, there are three different states, but the energy values are same. So This is and the next question. The question is similar to the thing what we are discussing. The question gives find the energy and degeneracy of a particle in three-dimensional infinite potential well. So here basically some part of the question is missing. Find the energy and degeneracy of the particle for a particle in fast ground state or second in fast excited state or second. We can take it as second excited state. Second excited state because we have already discussed about the fast excited state. So please think about the answer. What will be the values of nx and ny and nz, nx, ny and nz for the second excited state. I will give you some time to think about it, and then we will discuss not only about the second excited state but also the remaining states and their degeneracy. How many different combinations of wave function we can get. We will discuss about this. So please think about it. So we can. So the question is, find the energy and degeneration of a particle in three-dimensional infinite potential well. So what we will do here, we will write the value of n, here the value of nx, ny, nz, and here energy, and here degeneration. So if n equals to, so n is nothing but nx plus ny plus nz. So here, for in case of one dimensional, if n equals to 1, so nx, ny and nz both were 1, all were 1, so energy was 3e1, and there was no degeneracy, that is degeneracy is 1. But when we go but when we consider the when we talk about the fast excited state, then nx, ny, nz value will be different. So it will be 1, it will be 1 2 1 2 1 1, and sorry, so the values will be 2 1 1 1 2 1 and 1 1 2. So there are three values, and the energy is 1 square plus 2 square plus 1 square plus 1 square plus 2 square, that is 4 plus 2 is 6. So it is 6e1. Here we are all considering about the symmetric potential box. That symmetric means in on all the sides it is same. That is A equals to B equals to C. It is, this is ground state. This is fast excited state, and second excited state will be how much? For second excited, similarly we can take here 2 2 1 1 2 2 and 2 1 2. So here it is also the three combinations, and the energy value will be 2 square plus 2 square plus 1 square, that is 8 into, so it is 9e1. But so in, so this is second excited state. For second excited state, the degeneracy is 3, and the energy is 9e1, because 2 square plus 2 square plus 1 square is 9. And third excited state, so third excited, what will the value? There are two twos, but here, then here it will be how much? It will be three twos. But if you see here, when you, so if you see here, when you take nx and ny and nz all 2, then it will be how much? 2 square plus 2 square plus 2 square, that is 4 plus 4 plus 4 is 12. So it will be 12e1. But if you think about the combination 311 or 113, then that then it will give how much? It is 12 e1, but here it will be 3e1, 3 square plus 1 square plus 1 square, so 9 plus 2 is 11, so it will be 11e1. Since 11e1 is smaller than 12e1, so for third excited state, so for third excited state, the possible combinations of ny, nz and nx, ny, nz are 3 1 1. So it will be 3 1 1 1 3 1 and 1 1 3. So the energy will be how much? Energy will be 11e1, and the degeneracy will be 3. And if you talk again fourth excited state, then it will be all 2, because for fourth excited state, the next one will be all 2. So it will be 2, 2, 2. So it will be 12E0, and the degeneration will be 1, that is, it is non-degenerate. And again, if you talk about And again, if you talk about the fifth excited state, for fifth excited, the possible combinations of nx, ny, and nz will be 1, 2, and 3. So, because if you can see, if you take here 1, 3, and all these two are 2s, then it will be more than the value what the combination 1, 2, 3 will give you, because this combination 1, 2, 3 gives 3 square plus 2 square plus 1 square. It is 4 plus 9 is 13 plus 1 14, so it is 14 is 0. And the digits will be how much? Because if it's 1 2 3, it can be 1 3 2, 2 3 1, 2 1 3, 3 1 2, 3 2 1. So this is 6. There are 6 combinations, possible combinations. So the degenerate is 6. So like that we can calculate the. So we can calculate other excited states. This type of question comes in net and gate exam. So please understand it carefully. These are the basic possible combinations of a particle in three-dimensional infinite potential box. So for three-dimensional infinite potential box, the ground state will be Nx, Ny, Nz all are 1. So the energy is 3U1 and dGns is 1. For fast excited state, it is 6U1 and dGns is 3, because Nx, any one of the numbers Nx, Ny, and Nz will be 2. So 2 square plus 1 square plus 1 square will be 4. I'm again repeating 2 square plus 1 square plus 1 square, because here we can see the energy value is Nx square plus Ny square plus Nz square. So here 2 square plus 1 square, it is 6E1 and dGns is 3. Similarly, for second excited state, there are two 2's, so it will be 9E1, and also there will be 3 different combinations. And for third excited state, it is 311, so it will be 11E1 and there will be 3 degeneracy 3. For fourth excited state, it will be 2212, 12E0, 12E0 or 12E0, and third DNS will be 1. And for fifth excited state, it will be 14E0, and the DNS will be 6, because there are the all the values of Nx, Ny, and Nz are different, that is 1, 2, and 3. So from 1, 2, and 3, there are 6 different combinations. So the DNS will be 6. I think this is clear to all of you. We can go to the next question. The question is, the electron of the hydrogen atom is in its ground state. Determine the expectation value of R in terms of Bohr radius A0. This is basically the expectation value. This type of question we had solved it in the previous sessions, so we can easily do. We can easily solve it. This is one of the postulate of quantum mechanics. So in quantum mechanics, what we calculate, we don't calculate the exact value, we calculate the expectation value, and the expectation value of a certain quantity is known as, if a is a certain value, then its expectation value is. So the question is, the electron of the hydrogen atom is in its ground state. Determine the expectation value of R in terms of Bohr radius A0. So we know that in quantum mechanics, any quantity we can calculate its. We can't calculate the exact value. We calculate its expectation values, and the expectation value of a quantity A is uh, psi star a psi star a psi into dx if it is one dimensional. So a is the operator, and the uh, expectation value of this operator is calculated by integrating the function psi star a cap psi dx. So if it is since we are calculating the expectation value of r, which is a three-dimensional quantity. So the expectation value of r will be how much? The expectation value of r will be integration psi star r psi star r and psi dr dqr. And we know for spherical polar coordinate the volume term, that is dqr, will be dr d theta d phi into r square sin theta, because uh, in case of spherical polar coordinates, the h1 is 1, h2 is r, and h3 is r sin theta. So there will be h1 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 dr, h2 d theta, and h3 d phi. So the volume element will be dr d theta d phi into r square sin theta. So when you put all these value, and since it is given the electron of the hydrogen atom is in its ground state, so for ground state the wave function will be of ground state wave function. So the ground state wave function, the value of n is 1, L is 0, and M is 0. So the wave function will be psi 100. In the first question of today's session, we had discussed the wave function of 100 is how much? 1 by pi aq root over exponential minus r by a0. Here it will be a0 again, because it is given the Bohr radius in terms of the Bohr radius a0, expectation value of r, and the electron is in ground state. So for ground state the wave function is 1 by pi aq root over e to the power minus r by a0. So when you integrate it, then what will be the expectation value? The expectation value of r will be integration 1 by pi aq root over e to the power minus r by a into r into again psi. This is psi star, this is r, that is a, then it will be psi. Psi is 1 by pi aq root over e to the power minus r by a dr. So if we can separate the integrations, so this term only r dependent, and the next will be d theta, and there is another r square term, so it is r square, it is d theta sin theta, it is d phi. So here the expectation value will be, for r it will be 0 to infinite, because r don't have negative values. For theta it will be 0 to pi. For phi it is 0 to 2 pi, because in spherical polar coordinate, what is there in spherical polar coordinate, this, if this is a spherical polar coordinate, from here to here it is r, then this portion makes angle pi, this is theta, and this portion, the long, we call this as longitude and latitude. So this is theta and this is phi. So this is phi, and this it is theta. So theta varies from 0 to pi, but phi varies from 0 to 2 pi. So This is the integration, and if you integrate it, we can get the value. So please do the integration and tell me what will be the expectation value of R in the ground state of hydrogen atom. I'll be waiting for few minutes, then I will solve the integration. Yes, the value will be 3 by 2 A0. So um, do I need, no, it is 3 by 2 A0, it will not be 3 by 4 A0. So it will be 3 by 2 A0. So should I calculate or you can calculate it? So then we can proceed to the next question. So let's calculate it once again. The This is the integration, and we know this part of the integration, that is d theta sine theta, and the d phi. This is the solid angle, and solid angle is 4 pi. So these two integrations gives us 4 pi. This is 4 pi. We only need to integrate the radial part. So when you integrate the radial part, what will be the integration value? So this is 4 pi, and the integration is 0 to infinite. This is r, this is r square, so it will be r cube a to the power minus 2r by a e to the power minus 2r by a, and this is 1 by pi a cube root over 1 by pi a cube root over, so it will be pi a cube, so it will be pi a0 cube. It will be a0 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 into dr. There is a formula for this integration, and the formula is
From integration minus infinity to if the integration formula is the integration formula is integration integration 0 to infinite r to the power n e to the power minus alpha r dr equals to how much n factorial divided by alpha to the power n plus 1. Sorry. So it will be n factorial divided by alpha to the power n plus 1. So here in this question n is 3 and alpha is how much? Alpha is 2 by a0. So when you put all the values, what will be the integration value? The integration value will be 4 pi by pi aq was already present there. It will be n factorial, that is 3 factorial by 2 by alpha 0 or a0. It is 2 by a0 to the power 4. N plus 1, that is 4. So when you calculate it, it will be how much? 4 pi by, sorry, it will pi will be cancelled out. Pi will be cancelled out. It will be 4 by a cube into 0 factorial 6 by 2 to the power 4. 2 to the power 4 is 16 and it is a0 to the power 4. So 4 into 4, it is 2, it is 3. So a cube and this just cancel away. It will be 3 by 2 a0. So the expectation value of R in the ground state of hydrogen atom. So the expectation value of R in the ground state of hydrogen atom will be 3 by 2 a0. Similarly, so this is the question. The question was we want to determine the expectation value of R in the both R in the ground state of hydrogen atom in terms of both radius a0. So the expectation value of so in this class in the beginning we discussed about the most probable value of the position and we got here and we got there the for ground state the most probable value is R, but the expectation value is 3 by 2 uh, the expectation value is 3 by 2 a0, that is it is greater than a0. So the electron can be present anywhere from 0 to infinite and the most probable value of the position is r equals to a, that is at r equals to a there the particle is majorly found, but the expectation value if you take all the possible probabilities or possibilities, then the value is 3 by 2 a0. Similarly we can calculate other expectation value, that is expectation value of 1 by r. We can calculate for hydrogen ground state. The expectation value of 1 by r will be 1 by a. Expectation value of 1 by r square will be 1 by a square. The expectation value of r square will be 3 square, like that. So this is the different expectation value. So please verify these calculations. It will help you to do the calculations faster in other exams, because is here it is given the ground state of hydrogen atom, so you are using the ground state wave function, that is wave function. Here the ground state wave function, we are using the ground state wave function, and the ground state wave function is psi 100 equal to 1 by pi a 0 q e to the power minus r by a 0. But sometimes in exams the question may come where the wave function will be different, and it will be given to calculate the expectation value of this quantity, of a certain quantity in this state. So what you have to do there, we will put the wave function value here, the given wave function value, and you will calculate. As here it is given the atom is in ground state of hydrogen atom, so we know the ground state wave function of the hydrogen atom, and we are putting the value of the ground state wave function. So in this way you can solve different other types of expectation values, and you can calculate the and you can calculate their values. So do you have any doubt in this question, or should I proceed to the next question? Anyone? Does anyone have any doubt in this question? I think do you don't have any doubt, so we can proceed to the next question. So these are basically the atomic spectra part. Then we can go to the molecular spectra part. Sorry, once again. Eigenvalue is what is eigenvalue? Eigenvalue is something. Eigenvalue. Let me explain you. Hmm. Eigen equation is what is Eigen equation? When we operate a certain operator with that when we operate a certain operator in a particular state, and we get the get a real value and the state remains unchanged, then in that case we can we called it a is the eigen value of the operator a. So a is the eigen value. And generally operators, there are different types of operators, linear operators. There is other operators which are called as Hermitian operators, and for Hermitian operators the complex conjugate, that is the dagger, we call it a dagger, this is equals to a. So and in that case the eigen value, if you put here, when you put these values here, then this is the eigen value equation, that is a cap psi equal to a psi. Then if a is Hermitian, that is a dagger equals to a, then in that case you will found we will found a equal to a star. Since a equal to a star, that means a and its complex conjugate both are equal. So it will be possible only when a is real, is not it? Because if you are taking a equals to 2i, then a star will be how much? A star will be minus 2i. So here it is a not equal to a, but here if a equal to 2 only, then here complex conjugate will be again 2. So if a is real, then a and a star both will be equal. So it is told that if an operator is Hermitian, the eigenvalue associated with that operator is, so the eigenvalue associated with that operator is real. So basically this is the thing about the eigenvalues. So when you operate a operator in a state, and we get the eigen and we get the same state back, and the eigenvalues is the remaining value, here is the eigenvalue. So this is the case. We have discussed few problems regarding the eigenvalues. Let me search for that problem.
we had discussed the eigenvalue of some quantity we had calculated. So in previous class we calculated eigenvalue of a quantity, this question. So in this question what we did, we calculated find the eigenvalue of linear momentum operator in the state. So here this is the state and we want to calculate the eigenvalue, and we know that eigenvalue is what, if we operate an operator in the same state and the result we got in the same state, that is if we are operating in a state psi, in the result we will get the same state psi with another additional quantity, and that quantity is the eigenvalue. So this is the state, and the operator linear momentum operator is this one, minus I x cross del by del x. So when you operate this, that is when you take the derivative of this state that with respect to x, that is we operate the operator px cap on psi, that is minus I h cross del by del x of psi. So when we take derivative and we do the do all calculation, we can see here this a exponential I 2 pi lambda by h into x, this value is there. This is nothing but the wave function itself. So when you are operating the operator on a wave function, the wave function is remaining unchanged. You understand, the wave function is remaining unchanged, but the some extra value we are getting along with the wave function, this value is lambda. So the eigenvalue of the, so the eigenvalue of the state, the eigenvalue of the linear momentum operator of the state psi is lambda. So we can take another example which will, yes, yes. I think I had also discussed that question. In that question, what we are in case of hydrogen atom or any other potential. So that question energy agent value will be calculated by taking the help of. Uh, Let me add another slide. So when you are given an wave function and a potential, there must be some potential given, because without potential you can't calculate the eigenvalues, because we need to see for energy eigenvalue we need energy operator. So for energy operator is known as Hermitian operator, h cap psi is equals to h psi is equal to e psi. This h is Hermitian Hamiltonian operator. This is Hamiltonian operator, and this is total energy operator, otherwise called the name of the total energy operator, otherwise called as Hamiltonian operator. So it is total energy operator, and its eigenvalue is E. So if you operate the Hamiltonian operator on a wave function psi and you get some value here, and and this wave function psi is again produced here, then we call it as the eigen energy value. And we know the Schrodinger equation is nothing but this equation. This is equation is Schrodinger equation, that is SI equal to E psi. When you put the value of H here, H is how much? If we are talking about one dimensional potential, then H will be px square by 2m plus Vx, because this is kinetic energy, this is potential energy. So when you put Px, we just discussed Px in quantum mechanics is equal to minus IH cross del by del x. So the Hamiltonian will be how much? Minus h cross square by 2m del square. This is minus x square by 2m. This del by del x square will be del square by del x square. So it will be del square plus Vx of psi will give you some value with psi. So when you put the form of the potential here, potential may be in exponential form or any other type of form. So when you put the exponential value here and you operate the operator in the wave function that is given by the state psi, that is here. So simply we can consider an example. Suppose psi is a sine kx. Okay, so if you want to calculate, question maybe, and suppose this is an operator, and the question it is given that calculate the eigenvalue of the operator in the state psi. Are you clear about the question? So in this question, psi is the state. The state is a sine kx, and the operator is del by del x. So when you operate it on the wave function psi, so when you operate it on the wave function psi, then what will be the equation? It will be a cap into psi. A cap is del by del x of psi. Psi is how much? Psi is a sine kx. So del by del x of a sine kx. It will be how much? A cos kx into k, is not it? So here you can see the sine kx is changed to cos kx. So the wave function psi get modified to another wave function psi prime, where psi and psi prime are not equal. So we can write this a cap psi equals to k psi prime. This is a equation, but this is not an eigen equation because psi and psi prime are not equal. But if you consider an example where we can take the operator a cap is nothing but del square by del x square. If this is an operator, then in that case, what we can do, we can take derivative twice. So in that case, a cap psi will be del square by del x square of a sine kx. So when you take first derivative, it will be a k cos kx del by del x. Then you take again derivative, it will be how much? Minus k square a sine kx. So you can see this a sine kx is nothing but the wave function psi. So this is wave function psi. So what we got here? We got here a square, sorry, a cap psi is minus k square psi. So here psi both psi are equal. So for the operator a square minus k square is eigenvalues, because when you are operating the operator on the state psi, the state is remaining unchanged, but it is giving a value of the operation. So this is the eigenvalue of, this is eigenvalue of the state psi. So we can see that the state a sin kx is not an eigenstate of operator del by del x, because the state is getting changed when you are operating it, but the state a sin kx is an operator for del square by del x square. So this state and this operator, these are, this operator is an these state psi equals to a sin kx is an eigenstate for the operator a cap equals to del square by del x square, but this operator is not an eigenstate for, this state is not an eigenstate for operator del by del psi, del by del x. Is it clear? So this is the case. I think there was a question in GATE a few years back, 1 to 2 years, and this was the question. The state was given, and the question was, there are different states, and the operator was given. The operator A cap was del square by del x square, and the question was, which of the following states is an eigenstate of this operator? So one of the option was a sin kx. Similarly, a cos kx is also possible, is not it? Because when you take first derivative, cos will be converted into sine, and then if you take again derivative, sine will be converted into cos. But if you take the operator a cap is equal to del by del x, then if you take psi is equals to exponential alpha x, suppose wave function is exponential alpha x. So when you operate, it will be how much? Del by del x of exponential alpha x. Taking the derivative, we will get how much? Alpha into exponential alpha x. So this exponential alpha x is again produced, so it is psi. So in that case, we are getting a psi equal to alpha psi. So this operator del by del x, this operator del by del x is an the state exponential alpha x is an eigenstate for the operator del by del x. So this is this state is an eigenstate for the operator del by del x, and this is an eigenstate for the operator del square by del x square. Now we are clear about it. So this is one set of example where a cos kx is the eigenstate for del square by del x square, and this is another set of example where the state exponential phi x is an eigenstate for operator del by del x. Is it clear to you? Okay, so I hello, yes. So I think we should stop here. In the next session, we will start the questions of molecular spectra. We will solve different questions on vibration rotational spectra and their significance. So thank you for in joining today's session. Have a great day. Bye.